Hi, this is Advanced Math, Chapter 12 on Vectors, Part F, pages 4 and 5. So, the last page, we introduced the idea of a vector equation, and I'm going to talk, well, the pages 4 and 5 are mostly exposition on that topic and some examples. And I've got one example at the end of page 5 and then more on 6. So, I'm just going to talk a little bit about what's written here, not to add much, but clarify what the intent of all of this is, I hope. So there are two different terms that you're going to be seeing, parametric equations or vector equations for a line. And these two concepts, parametric and vector equations, are very, very closely related. To write a parametric or vector equation for a line, so again, this is a way of writing a line equation in 3D or 2D, but it's really the best way to do it in 3D. You need to know the coordinates of a point that the line passes through, whether this is two-dimensional or three-dimensional. So just as you have in the past when you're writing the equation for a line, it's helpful to know where the line goes. So if you have the coordinates of a point the line passes through, that's going to be very helpful for both parametric and vector equations. And secondly, you need a vector that represents the velocity of the particle. And that can just be an expression of the direction of the line. It doesn't actually need to be modeling something moving through space. That direction vector is just a way of expressing a direction. The velocity vector is just a way of expressing the direction. So for example, a direction vector or velocity vector 1, comma 2, in terms of its direction would be identical to a direction vector of 2, comma 4. So any scalar multiple of one vector is the same direction, no matter, any vector times 5, it's going to be the same direction as that original vector. So here we have an example, as you might see. Let's write a vector and a parametric equation for a line that passes through a point, 6, 2, and has a direction that's a vector 3, comma negative 1. So we'll write it, the vector equation. Remember, vector equation has vectors instead of variables and constants, with the exception of the independent variable t. So the left-hand side of the equation is just that vector x comma y, or if you're in 3 dimensions, x comma y comma z. What would have been the slope in a y equals mx plus b format equation is that velocity or direction vector, which we were given here, times that independent variable t, plus an initial point or a point that the line passes through. Anything that you would be reasonably comfortable saying that's where this point was when time was equal to 0, we can use that. So we're saying that we have an equation for a line that passes through 6, 2 with this direction. So you end up with an equation that looks like this. Initial value 6, 2 and a slope or velocity vector of 3, negative 1. And one thing you can do with an equation like this is you can use it to figure out where the object or particle or bird is for a given time. For example, if we want to know where this particle slash bird is at 3 seconds, you take your vector equation and you substitute a 3 for the time. Now that just means you've got a vector multiplied by a scalar, so you multiply each of the components of the vector by the scalar. So this becomes 9, comma negative 3. And to that you add your initial vector and you get this sum, which is again the components independently added together. So 9 plus 6 is 15 and negative 3 plus 2 is negative 1. So this is a vector that represents the position of this particle bird at 3 seconds. Or stated in English, the particle will be at 15, negative 1 at t equals 3 seconds. Now, parametric equations. All we do is take the vector equation and split it into its x and y parts. So, for example, in this vector equation above, you take the x part, here's an x, write it down there. Here's the slope vector part, the x part of that, write that here. Take that independent variable, bring it down as well. And here's the x component of the initial position vector. Bring that down. So now you have a single equation It's not a vector equation anymore, but it's only for the x component of the situation. It's describing the motion of the x coordinate of the particle slash bird. And the y part is taking the y parts of the vector equation. So we take the y, the -1, the t, and the 2 from the vector equation and write them as a single equation. Y equals -1 times t plus 2. So now we have an equation that describes the change or the y coordinate of this particle slash bird as a function of time. All right, next page. Finding Cartesian equations from parametric equations. So suppose you've got this vector equation of particle slash bird. Um, what can we do to find if you're working in 2 dimensions, what's the sort of conventional equation for the line that would be equivalent? Um, and so when doing this, what you can do is you've got 2 equations. You've got this x equation and you've got the y equation. And for any instant in time for this particle moving along a line, the time in this equation is the same as the time in this equation. So if you can rearrange this equation to solve it for time, and rearrange this equation to solve it for time, you can set this equal to this. So those become, and then if you set this equal to this, you have a single equation that has x and y, and that is going to be a linear equation like the ones you're used to. So this is an example of doing that. You're setting time equal to time, t equal to t, which means you're setting this equal to this. So you have this equation. You can rearrange this using algebra and get y equals -1/3 x plus 4. So let's go down and try an example. Let's write this, and actually we're only supposed to write a vector and a parametric equation for this baby. Okay, let's do that. So vector equation, vector equation will start with a vector, x comma y, and this is the vector equation, equals. Now, the next thing, like y equals mx plus b, that m is the rate of change of position with respect to time, and that is the direction vector, also known as the velocity vector. So I'll take this and write it, -5 comma 4, and that's multiplied by the independent variable, which is time, and we'll add to that the initial position, or a position that this line passes through, which is given to us as 2 comma 3. And we're writing it as a vector because we're thinking of this point 2 comma 3 as a vector from the origin to that point. So now we truly have a vector equation where all of the components are vectors except for the independent variable. Now to write it as parametric, we want to break this apart into its separate x and y components. So we'll take the x parts and underline them in red, and we'll take the y parts and underline them in blue, and we'll break it out. So the x part, x equals -5t plus 2. The t actually is both, works for both x and y. Okay, so now for the y part, we take the y, all the blue pieces, 4t plus 3. And there you have the 2 different ways of representing this situation, both as a vector equation and as a pair of parametric equations. And if we did this in 3 dimensions, you'd have 3 equations here, one for x, one for y, one for z. All right, next page is going to be some more examples.